Well, if you can remember from the very first part of our video, we stated that the natural number e can be obtained by adding the reciprocal factorials of all natural numbers. But did you ever wonder why it's like that? And by the end of that video, you will understand it.
Also, we talked about a beautiful identity. It's e to the power of pi I is equal to -1, and I find it quite adorable because e is an irrational positive number raised to the power of pi, which is also an irrational positive number, multiplied by -1, like a square root of -1, which is a non-real number, is equal to a -1, a negative integer number, and I find it quite beautiful.
Also, in the first part of our video series, I talked about that e to the power of pi times I equals to -1. And in this part, we will talk more about complex numbers and we'll try to prove this beautiful Euler's identity. So let's dive in.
Maclaurin came up with an idea to represent any function as an infinite power series, given that this function is differentiable infinitely many times at this given point. Now Mr. Elnur will show you how to derive it.
Now we'll try to explain the Maclaurin series. Now the idea of Maclaurin series is to express any function, if it's possible, as the series, as the polynomial. So we have a function, f of x, right? That could be any function, sine x, cosine x, ln x, tangent x, or maybe composition of these functions. We want to express this function as a polynomial. So something like this, squared plus a cubed, x cubed plus a4, x to the power of 4 plus so on. So by the way, if you're not familiar with the term polynomial, polynomial is just the sum of the terms where x has non-negative power, non-negative natural power. Okay, so now the main question is how we can find the coefficients a0, a1, a2, a3, and so on. Now let's start with the a0. Think about, now the question to you, to the audience, how can you find the coefficient of a0? And it's very easy, by the way. Don't dive deep into the depth of mathematics. It's very easy. Yeah. How you can make all this stuff to disappear and you're gonna left with a0. Now, maybe you may answer.
Yes, we can find f of 0 and all x's will disappear and we will be left only with the first term.
Great.
It's like a y-intercept of a linear function.
Yeah, so a0, let me write here, it's just we plug in f of, we plug 0 everywhere here, so we'll be left with a0. Great. Now, we're done with this one. Now this, how we can find the coefficient a1. That's a little bit trickier. That requires, I think, ingenuity, some new technique, how we can find a1. Any ideas?
Second chance.
Yeah.
Well, the first thing, if you plug 0, this will disappear. We don't want this to happen. If you plug, for example, any other number, we'll have other terms as well,
Yeah.
which also will not work.
Yeah.
So if you're talking about calculus, perhaps we should use differentiation, because if you differentiate it, this will disappear because it's constant.
Yeah.
And all other terms apart from this one will have an x term.
Okay.
And if we plug 0 in its first derivative, maybe.
Good. Yeah. So first we find derivative. Oops. X here. This will disappear because derivative of a0, the derivative of any number, remember it's not the letter, it's a number. And derivative of any number is 0. So we'll move here. Here derivative of x is 1, so we're left with a1 plus, here we apply the rules of differentiation, 2 will come in front.
And we'll decrease the power by 1.
Yeah, and the power will be decreased by 1, so it's x to the power of 1. I'm not gonna write that. Plus 3, okay.
Or a with a subscript of 4 times x to the cube. Yeah.
X cubed plus so on. I think I didn't manage to write it correctly. F of 0 is What was? A0. So that's our first result. So now, yeah, now we found the derivative, right? And the question is how to find A1. And we applied the same thing that we've applied earlier in order to find A1. Yeah, we need to get rid of these x's, and the best way how you can get rid of the x, just substitute 0 for x's. So let me write here. F of, no, not here. I changed my mind. Here. F prime of 0 is just A1 because all this stuff will disappear.
Yeah.
Good.
So we've already found two coefficients.
Yeah.
So we shall repeat the steps maybe?
Yeah, maybe let's continue. Let's apply the same thing. Let's find derivative of this expression. So it's the second derivative. So this will disappear because it's a number.
It's 2A2.
Here, derivative of x is 1.
2A2, 6, 3 by 30, A3 x to the power of 1.
Okay, so what we did here, 2 moved in front. Then we decreased the power by 1. Again, that's the rules of differentiation. Now we'll do the same thing here. 4 times 3, we move 3 here.
A4 6 squared.
X to the power of 2 because we reduced by 1. So again, we need to find this. In order to find this, we need to get rid of all this stuff, and how we can get rid of all this stuff is just to substitute 0 here, here, everywhere. So let me write here. So second derivative at 0 is 2A2, and that means that A2,
Second derivative divided by 2.
yeah, that's an achievement because we already know the value of this coefficient, the value of this coefficient, the value of this coefficient. It's great. We just apply this infinitely many times if we have time. We apply several times, and then we're gonna find the rest, all the other coefficients.
Yeah, but the problem is we don't have time, so
yeah,
what shall we do?
yeah. We'll do one more.
Almost an infinity.
Yeah, almost close to. Okay, so we will find the next, and I think the next will be enough.
Okay.
By the next, we'll figure out the pattern because maybe somehow you understand. Maybe you can guess what will be the next A3. What is the A3? But just to think about some expression. What do you think? What your heart tells you? What is the A3? Yeah. So, this term will disappear because it's a number.
So it's 3 times
I move here.
3 times 2.
Again, x disappears because derivative of x is 1 plus
4 times 3 by 2. Just x.
X because we reduce the power by 1 plus 1, and we do the same thing. How to find the coefficient A3?
Plug in 0.
Just plug in 0 so that all this stuff, because all this stuff will contain x in themselves, and they will disappear. So the third derivative at 0 is 3 times 2 times A3. And there is a reason why I don't multiply this, by the way. Why I don't write 6. I write 3 times 2. So the reason is we don't have time to multiply this all the time, because the next is 4 times 3 times 2. The next will be 5 times 4 times 3 times 2 times something times 1, and that's a spoiler.
Yeah,
maybe you can figure out how we can replace these so that we don't have to multiply. That's 6, that's easy. The next one is 24, that's also easy. But the next
120?
ones, 120, 720.
No.
The next, I don't know. The rest, it's, yeah, something like that. Yeah.
15, yeah, 54. Anyway.
That will be like difficult to count. How we can replace this by the more easier thing, and the hint here is that we add here 1, because 1 will not change anything. 3 times 2 times 1, and if you remember in the previous hour series, we replaced 3 times 2 times 1. We talked about what is 3 times 2 times 1.
Yeah.
Yeah?
It's a factorial.
Good. So we can replace this by
3 factorial.
3 factorial. So in order to find a3, I move it here. So it's a third derivative.
So does it actually mean that this 2 is a 2 factorial?
Yeah, because you can count by yourself. 2 factorial is just 1 times 2.
Yeah.
That's 2. So we didn't do anything.
Is it? Yeah, divided by 1 factorial.
Yeah, because 1 factorial is nothing. It's just 1.
And
so it
one
doesn't
more
change
terrible truth, like, is it divided by 0 factorial?
Yeah, for the sake, like, to
Cringe,
continue
like.
the pattern,
Yeah.
just for that reason, no other reason. Because I don't like writing this.
Actually, we also don't like it.
Yeah.
Because
but
is it like 0's derivative? It's kind of weird.
Yeah. Ugh. So, just to make the pattern clear here, now we can find the next coefficient. Even if we don't apply this thing, we can figure out what will be the next coefficient, and the next, and the next, and the next, and then we can generalize. Patterns are very important things. So what we do now? Let me copy this, but let me replace the coefficient because I know them. But let me do this here. So I don't need this stuff. I only need coefficients. So our function. Remember, this is some crazy function like sine x, sine ln x inside maybe over something else, maybe some not beautiful thing, and we replace this by its polynomial. So it's gonna be a0 plus a1
f prime of 0 by 1 factorial, and continue like with the same,
plus a2
this f the second derivative, and by x squared.
Okay, here is this. So a3.
Yeah.
And we can even continue, right? So figure out, maybe you have already figured it out, what is the next term here. Just continuing the pattern. You see, now the pattern is, you see the order of derivative is the same as the factorial, and that's the same thing as the
Exponent of x.
Yeah, exponent of x. That's I think that's beautiful. I think I mean, here it happens the same thing, like the order of derivative is the same as the factorial and the same thing as the power of x. Now we can continue.
The fourth derivative divided by 4 and x to the fourth. Yeah.
It's kind of not that difficult, right? When I first heard Maclaurin series, I thought that's something very scary, maybe difficult, but it's not that scary. I mean, you can remember, like if you do this 2 to 3 times, you'll remember. Now, let's generalize this. What is the nth? What happens if I find the nth derivative, right? So the nth derivative will, that's not x, that's 0, will be divided by n factorial, right? Because they should be the same. And multiply by of n. And
So
we will have infinitely many terms. The more terms you have, by the way, the closer you can get to this, to the original function. So the more the terms, the better your approximation. So what we did, we expressed the function, any function, by the polynomial expression. Why we did this? Because it's easier to work with the polynomials. It's easier to find their derivatives. It's easier to find their integrals. It's easier to, I don't know, add them, subtract them, multiply them. It's easier to work with them rather than with these kind of expressions. And we'll use it in our next journey, let's say that. That's it.
There is a specific set of functions called trigonometric functions. For example, sine and cosine, both of these functions are used to define the behavior of waves. And actually, now Nurlana will show you how to write, how to derive Maclaurin series for both of these functions. So, let's pass on.
So, in the previous part, Mr. Elnur showed us how to write the Maclaurin's formula, and he showed us the clear explanations, and we came up with the idea how Maclaurin decided to write this formula in that particular way. Now, I would like to remind you about how Maclaurin formula looks like in order to remember it. So, the Maclaurin's formula is f of particular a plus f prime, the first derivative of this a, multiplied by x minus a, plus f second derivative of that a, multiplied by x minus a squared, divided by, I do not write divided by 1 factorial there because 1 factorial is just 1, but I write 2 factorial there because you remember we write the power there and divide to the same factorial, to the factorial of the same power, plus f third derivative of a x minus a cubed to the third power divided by 3 factorial. And if we continue, we see that we can write the fourth derivative, fourth power, 4 factorial, fifth, sixth, seventh, and so on infinitely many times. It has no end. And if we look at these graphs, particularly our purpose is to show you how to write Maclaurin's formula for sine of x and cosine of x. So if you do not know what is the derivative of sine of x or the derivative of cosine of x, let's see the graphs and compare them. We decided not to show you the ways that are very complicated, such as limits and other definitions of derivatives, but just to compare graphically. So you see 2 graphs there. Try to guess which one is sine of x and which one is cosine of x. Did you guess? I can write it. This is sine of x. This one is cosine of x. So let's see. First of all, you can notice that they are identical. They are similar, all of them, both of them are waves, but actually they are different. If you know what the extrema is, pause the video and write to the comment section. We'll read them carefully and give you responses. But now I would like to tell you, or maybe you know what is extrema from your overall knowledge of calculus or any other resources, it doesn't matter. So extrema is the highest point the y can achieve or the lowest point. So this is our y-axis and this is our x-axis. You can see that there are 2 maximum points if we take the period of 2p and 2 minimum points, maximum extremas and minimum extremas. So we can see that these are the highest points, and there are when we have negative 3p divided by 2 and p divided by 2, which are actually 90 degrees and negative 270 degrees. And the lowest points are when we have negative sine of p divided by 2 and 3p divided by 2. Well, these 4 points, let's now see what these points say us about cosine of x. You can see negative 3p divided by 2, okay, negative p divided by 2, okay, p divided by 2, and 3p divided by 2. These are 4 extremas of sine of x. We can see that all 4 of them are equal to 0 when we have cosine of x. So if you know the definitions of derivatives or their properties, you may know that if one function has extremas at these particular points and another function has zeros, they are probably derivatives of one another. And we can assume that cosine of x is derivative of sine of x. But do not think that sine of x is derivative of cosine of x. No, it's not the same thing. When you can see that when sine of x is increasing, cosine of x is more than 0, and when sine of x is decreasing, cosine of x is less than 0. But it's not same thing reversely, because when cosine of x increases in the first quarter, sine of x is decreasing. That's why if we write derivative of cosine of x, we somehow negotiate and write negative sign. So what I want to tell you more about their derivatives, I don't know what to tell, but I can mention also that cosine has maximum points at and lowest points at negative 2p, negative p, 0, p, and 2p, which are actually equal to 0 when we have sine of x. Let's now proceed with writing Maclaurin's formula, and for this purpose I would like to erase these two graphs. Let me erase them at first and see how we can write Maclaurin's formula for sine of x first and cosine of x then, secondly. Okay, so first of all we have to write their derivatives. Let's take our function, first function, f of x is sine of x. Let's write its derivative, f prime x. Well, you now know that its derivative is cosine of x. Also, I advise you to remember that sine of x's derivative is cosine of x, and the derivative of cosine of x is negative sine x. Let's continue. Let's write third derivative, which will be actually, do not look at the negative sign there, look at the sine x, it's cosine x, but we have negative sign behind sine, and we add this to cosine of x. So let's write fourth derivative. Cosine of x is negative sine of x. We see negative sign behind cosine of x. We add one more negative. Minus plus minus gives us positive sign. It's just positive sine of x. So we continue with the fifth one, and I will stop with prime x, which is actually cosine of x. And you can probably catch the pattern now, because the first derivative is the same as the original function, our initial value, and cosine of x is fifth derivative is the same as first derivative. So to expand this Maclaurin's formula, we have to substitute zeros. Let's do it right now. So let's now substitute zeros. If I substitute sine of 0 is just 0. I write it there. Cosine of 0 is 1. It's equal to 1. Negative sine of 0, negative 0 is just 0. That's why I write there 0. Negative cosine of x is 1. Negative sign behind cosine, negative 1. Let's continue. Sine of 0 is 0. And cosine of 0, well, it repeats with this initial function. Cosine of 0 is 1. That's why it repeats there. And if I write sixth derivative, I'll get again 0, 7th negative 1, 8th 0, 9th 1, and so on infinitely many times till the 100s, 1000s, and so on. So you can catch the pattern there, because we see that it somehow alternates 0, 0, 0, and it changes between 1, negative 1, 1, negative 1, 1, and so on. So if we substitute these values in our Maclaurin's formula, we'll get something interesting. Precisely, we'll get Maclaurin's formula for sine of x. So let me continue from this space, and I will substitute all the values in order to get our formula. So f of a is f of sine of x, which is 0. It will be equal to 0, and I do not write 0 plus anything. I continue with cosine of x. I'll get 1 there. X minus 0 is x. I'll just get 1 multiplied by x, which is actually x. Plus f second derivative of a is 0. It will be 0, and it will be eliminated and disappear. It will be equal to 0. Let's continue with the third one, which is actually the fourth one in our row. Third derivative is negative 1. So I erase plus and change it to the negative sign. X minus 0 is x cubed divided by 3 factorial. Let me change the sign. Okay, let me write plus, and we'll see if it's plus or minus. So we can see that fourth derivative is 0, and it will also disappear, and fifth derivative is 1. That's why we'll get 1 multiplied by same thing to the fifth power divided by 5 factorial. Is x to the 5th power, fifth power divided by 5 factorial. Sixth one will be also 0 because it alternates. Seventh one will be -1. That's why I write again negative sign x 7 to the 7th power divided by 7 factorial plus. You can catch the pattern. If you know it, pause the video, think for yourself, and write in the comment section below what you think will be the continuation of it. So you can see that all even powers are eliminated. We do not have second power, fourth, sixth. We started from first, third, fifth, seventh, and we'll continue with 9, 11, 13, 15, and so on, infinitely many times. And we can also see another pattern that we started with a positive sign, switched to negative, positive, negative, now again positive. It will be x to the 9th power divided by 9 factorial minus x 11th power 11 factorial, and it will continue plus minus. The signs will change, alternate, and we will be left only with odd powers and factorials. This is our definition of sine of x. Let's now dive into cosine of x, which will be much easier. Why? Because I'll show you some tricks right now. You may also think for yourself what the cosine of x will be, because you got the point, you got the idea how you can write down the Maclaurin's formula for anything yourself. You just find its derivatives 5 times, 6 times, it will be visible for you when to stop, and just substitute them into the original formula. So if our original function is cosine of x, we just erase the initial function of sine of x, we erase it, and we change these primes there. Let me change them. It will be original function, first derivative, second derivative, third, fourth, and I can add fifth derivative, which is negative sine x, because derivative of cosine of x is negative sine x. So it's the same thing there, and if I write negative sine x, it will be again 0. So let's do same thing to cosine of x. I know you may be very tired with all these things, but it's much easier. You can do it even yourself, but let's see what it looks like. Cosine of x is 1, so I write 1 there. I do not start with x, I start with 1 plus f of a, f prime a, is 0. This one disappears and I do not write it. Second derivative will be -1. Again, I switch to negative sign. It's 1, -1. And if a is 0, we'll be left only with x squared divided by 2 factorial. This is third derivative, which is actually 0. It also disappears. Fourth one will be 1, so we have there plus. We will be left with 1 there, x fourth power divided by 4 factorial. Fourth power, 4 factorial. And again, if we see, they'll be 0, is fifth one, sixth one will be -1, 0, -1, and these signs will also alternate. X to the 6th power, 6 factorial, plus 8th power, 8 factorial. You can even check it for yourself if you don't believe me. What we see there, how it is different from the sine of x, this actually cosine of x, is that sine of x started with x, it started from there, cosine of x started from the first one. The same pattern, it starts with positive, negative, positive, negative. What's also different that in sine of x we are left only with even powers, but in cosine of x we are left, we are left with odd powers, and in cosine of x we are left with even powers. That's it. We showed you how to write Maclaurin's formula for sine of x and also cosine of x.
From the first part of our video series, you may remember that the natural number e can be found by summation of reciprocal factorials of non-negative integers. Now we have enough resources to prove it, but first we need to derive what the Maclaurin series for e to the power of x is.
So now I will show you how to write the Maclaurin series for the function e to the power of x. So you remember this general formula that Mr. Elnur has shown to you earlier in this video. I'll just apply this formula to for one specific function e to the power of x. So let's start. So my function f of x is just a general term, will be e to the power of x. So the first thing I have to do, I have to find this term. We'll be going term by term. So f of 0 is e to the power of 0. I just have to plug 0 instead of x, and you know that any number to the power of 0 is just 1. Yeah, so I'll replace this term by 1 here. Then we have to find the first derivative of the function. So let's write it in Leibniz notation, d over dx e to the x. Hopefully you remember from the second part of the video that the derivative, that any derivative of e to the x is e to the x itself. So this makes this function special. Hopefully you remember that, because yeah, I have to plug 0 instead of x, and you know e to the power of 0 again will be the same as this, again is 1. So this term is 1. 1 multiplied by x is just x. I'll not write 1 multiplied by something. So then let's find this. This is the second derivative of the function. So I'll have to differentiate this function. Like the second derivative is the first derivative of the first derivative. So the first derivative is this, e to the x. So I'll have to, again, let's write it this way, d2 dx2, which is Leibniz notation for a second derivative, e to the x, again e to the x itself, x is 0, and e to the 0 is just 1. So we know this term is just 1, so we're left with x squared and 2 factorial, so let's write. And as I'm writing this, you may have already realized what this derivative will be, what the next one, the 4th, the 5th, the n's, by the way, all of them will be equal to 1, because every time you differentiate e to the x, you get e to the x itself, you plug 0 and get 1. So it's quite simple. So let's write this term. We're left with x cubed and 3 factorial, x cubed over 3 factorial, plus, and so on and so on. Here we have x to the power of n as a general term over n factorial. And let's write sigma notation as well. So we notice that we have powers. Actually, 1 is x to the power of 0, this is 1, 2, 3, 4, 5, and so on until n. It goes from 0, like it starts from 0. Then we notice that the factorials on the denominator always correspond to the exponents of the x, so we'll have the same n factorial in the denominator, and actually it goes until infinity. So let's write infinity. So it was quite simple. Now we have the Maclaurin series expansion for the function e to the power of x. Let's now use this expansion to prove one thing from this first part of the video. Do you remember we said that the number e can be obtained by adding reciprocals of all natural numbers, like reciprocals of factorials of all natural numbers. So how do I get e from e to the x? Obviously I just have to plug x equals 1, right? And I'll have to plug x equals 1 everywhere I see it. So it's 1 plus x equals 1 plus 1 squared just 1 over 2 factorial plus 1 cube again just 1 over 3 factorial, and so on and so on. It goes until 1 to the power of n, 1 to any power just 1, so 1 over n factorial. And I can plug 1 here as well, so it will be it's a sum of 1 to the power of n. I will not write n because 1 to any power just 1, divided by n factorial. It goes from 0 to infinity. And this is a beautiful formula that we showed to you in the first part. So it's actually interesting how we can prove it right now. Yeah, so that's it. That's Maclaurin series and the proof of like that E is a converging series of factorials. Yeah, that's it.
Now we're gonna show the Euler's formula. The Euler's formula for this, first of all, we already showed that e to the power of x equals to this series, and it has the continuation. Now in the Euler's formula, we just substitute I times x instead of x. So I just substitute I times x everywhere. So I will substitute I times x here, I times x here, I times x here, everywhere. So it's gonna be 1 plus I times x, that's just I times x, plus I times x squared, all squared, over 2 factorial, that's I by the way, that's multiplication, plus that's gonna be I times x cubed over 3 factorial plus I times x to the power of 4 over 4 factorial plus I times x to the power of 5 over 5 factorial, and so on.
Well, probably now we can just simplify the terms that contain I, because we know some properties of complex numbers.
Yeah, exactly. Now we have bunch of i's here. I, by the way, is root of -1, right? So I squared, and we're going to use that, I squared will be just -1. When we square this, the square will be annihilated with the root sign, with the radical sign, and what will be left is -1. And also we need to know what is I to the power of 4, because we're going to need this. I to the power of 4...
It's like I squared squared.
Yeah, it's just a square of this, right? So that's going to be 1. So that's my
Makes sense.
1. And we also need I cubed, and we also need I to the power of 5. Now, think about, by the way, the audience, how we can simplify our I to the power of 3, because the answer will not be just a number, the answer will also contain I. We will not be able to get rid of the I completely, as in these cases. So think about what is the I cube and how we can express that. Now, any ideas from the audience here?
We can simplify it to the multiplication of different i's, I squared multiplied by I.
Good.
And because we know I squared is -1, we will just get -1.
Right? Great. So it's I squared is -1, so that's going to be -1 times I, and that's -I. And that's all we have. We cannot reduce it. If we cannot simplify it any further, that's what will be left. And I to the power of 5, we're gonna do the same thing again. Think about how we can express this as the product of two i's, so that we can get rid of the majority of i's. Like here you have 5 i's. You want to get rid of the most i's.
There are two ways actually. Either we could multiply I to the 4th by I, which will be I by 1, which will be I, or we could also write it as I cubed times I squared, which is -1 by -I.
Yeah, exactly.
Also give the same results.
Okay, I'm gonna use the first one, though it doesn't have any, it doesn't have any difference, whichever you want. So I to the power of 4 times I to the power of 4 is 1, so it's 1 times I, that's gonna be I. Yeah, that's all we have, right? So we can simplify this expression now. Now okay, now I continue this expression, right? So that expression equals, here's the equal sign, equals to 1 plus ix, here is not much thing I can do, it's I times x plus, that's gonna be I squared, and I squared is negative, so let me change it negative, so that's in place of I squared, and then x squared over 2 factorial plus, oh no, actually not plus, because I'm gonna have I cubed, and that is a negative I. So negative I, let me write like this, I x cubed over 3 factorial plus, I can write the plus now, I to the power of 4.
It's just x to the power of 4 divided by 4, because I to the first is just 1.
Yeah, because I to the power of 4 is 1. And again I have I to the power of 5, I to the power of 5 is, so it's I x 5 over 5 factorial plus. Now,
what if we isolate I?
Yeah, exactly. Now, what I do, I will isolate the terms that I have that contains I, and like collect the term that doesn't contain I in one side, and then collect all these things that contain I on the other side. So I have 1, then I have minus x squared over 2 factorial plus, and again using the our skill pattern recognition, you can continue this. By the way, you can predict what will happen next. So I'm gonna write minus da 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 da, and I will continue with these terms, the terms that contain I, and I will take I out of the brackets. I will have x minus x cubed over 3 factorial and plus x5 over 5 factorial, and again we can continue that as well, and I'm gonna write blah da da da.
Well, the thing that you have in the brackets, it's quite familiar.
Yeah, a second, think about what is this, and think about, not think about, but
Recognize, right?
Yeah, recognize, remember, because we've talked about this, right? So this is a familiar thing, and this is familiar thing, and that's why Maclaurin series is so powerful. You can recognize the Maclaurin series in different areas. Like here is the e to the power of ix, and surprisingly, now we have a Maclaurin series for, that's the Maclaurin series for what, guys?
Cosine.
Yay! Yay! That's the cosine x plus I. Actually, let me rewrite this. Cosine x plus I, and that's the Maclaurin for
Sine x, yeah.
sine x times sine x, and that's, let me copy that, and that is what is called the Euler's formula. That's it.
Well, Mr. Nur has already mentioned us Euler's formula, and now I would like to plug the value of pi into this formula and show you Euler's identity. So the formula looks like this: I to the power of e to the power of I multiplied by x, ix, is equal to cosine of x plus I multiplied by sine of x. Sine of x. So now I would like to plug pi into x's, and I'll be left with e to the power of pi multiplied by I is equal to cosine of pi plus I multiplied by sine of pi. So let me see, I don't change anything there. E to the power of pi I is equal to cosine of pi is equal to -1 plus I multiplied by sine of pi is just 0. This is -1. 0 0 gives us nothing. E to the power of pi I is equal to -1. That's it. This is Euler's identity.